Welcome everyone to another OCP tab call. This is call number 142. It's a pleasure to introduce today's OCP tab speaker, Jason, a hardware system engineer architect at Dell, where he focuses on advancing network solutions for modern infrastructure. Jason brings over 20 years of experience in communication technology with a background that spans hardware design, system integration, and project leadership across companies like Samsung, Nortel Networks, Silicon Labs, and several startups. He also has an he's also an active contributor to the industry standards through his work with the PCI-SIG CEM working group and the OCP NIC 3.0 project. Today's talk, Jason will walk us through an exciting and scalable approach to timing synchronization. This talk will explore how OCP NICs and PCIe adapters can be used to distribute timing signals and eliminating complex cables while enhancing system reliabilities. He also discusses how systems can automatically detect and enable timing capabilities of NICs, paving the way for advanced profiles like the G8265.1, G8275.1, and the G8275.2, all critical for robust telecom, edge, and data center deployments. Will you join me in welcoming Jason?
Yeah, thank you. Hey, Bob, Zona, nice to meet you. I think either we hear your printer or your Roomba going off. Thanks. All right. Hey, thank you very much for the introduction, and thanks, folks, for wanting to listen in here. Through the bio that was presented, it definitely brought me back to some of my first days as an engineer. My very first job was actually at Nortel Networks. So I was a base station hardware engineer focused on the T1E1 lines. So this is back when CDMA was brand new. We were going from 2G to 2.5G. And now we're here today at 5G, looking eventually here at 6G. So
Wonderful. Happy to
it
have you.
yeah, so it definitely, I have the gray hair for it and everything, and
Yes.
the scars, but all the joy from all that
Yes.
good advancements. I
Yes.
wanted to talk to everybody today about specifically, whereas we've been getting into 5G, one of the one of the biggest innovations that has been happening is, to be honest, and something I've been looking forward to is the commoditization of the digital side of the base station. As a former T1E1 designer, throughout my career, I've been involved in physical and some occasional wireless links. I've been really, one thing I've been seeing as a benefit of Ethernet is just how it has both commoditized and also scaled advancements and feature sets. And some of what I'm going to talk today is to try to help further that along within that. And at any point in time, as I kind of hit little pause moments in the slides, if you have any questions or clarifications you want me to make, feel free to jump in here. While I have a full deck, I have enough time where we can have some side conversations along the way. So within this discussion, I really want to focus on some of the current solutions that we have today with high precision clock profile support within server infrastructure. It's mainly going to be more of a telco focused conversation, but it does relate to other edge as well as financial markets that may benefit from high precision timing, especially if it's involved with data center server infrastructure. I also want to talk within that some of the recent additions in Ethernet adapter form factor specifications, specifically the OCP NIC 3.0, as well as the PCI-SIG recent advancements in the new, basically Chem 7. There's been some new updates that are relevant from time synchronization. I also want to talk about how these additions that I actually need your help in figuring how we're going to scale time synchronization, leveraging these sort of features. Doing so, I think you're going to see a lot more advancements happening. And given the fact that this particular subject is about timing appliances projects, I want to see what folks can benefit from these new feature additions to these form factors and how we can advance TAP within OCP. And then lastly, I also want to talk about some next steps on how to make that happen. Just to level set, which I think everyone I'd be shocked if no one knew this on this call here. But there's different computing synchronization options that's been around for a little while. The most simple, if you have a computing platform, you just need an accurate time besides having the real-time clock on your motherboard, is what's known as NTP, Network Time Protocol. It's been around a while. It's very useful. PTP, I know, has been off and on focused within these conversations. I won't get to it specifically, but this does relate to IEEE 1588 version 2, as well as 802.1as, the time-sensitive network. These will also benefit these sorts of protocols within these new feature additions. Past couple of years, there's been the precision time measurement, PTM feature. I know that's been discussed in past conversations that y'all have had. I'll touch a little bit on how this particular set of features benefit from it. And then lastly, the ITUT clock profiles that, all the G specs that relate to how these are implemented. We'll get a little further into that. The reason I want to at least bring this up is, from top to bottom, from top, it's just mainly software. And in the case of PTP, you may need a little more advanced hardware, like in a NIC, to make that happen. But as you keep scaling downward and advancing forward, there is a bit of a harmony between software and hardware that needs to happen to make these a complete solution. And so while I'm going to be very hardware focused at the beginning, I do want to be having everyone thinking about how as a solution we're going to make this work with software too. And I just gave kind of a brief list here. I know many other clock profiles that you guys could probably name here, but they may or may not relate. You just kind of have to decide that for yourself. So let's talk about why some of these new additions have been added. I think the best one I can point to is one of the contributions that the OCP TAP group did was this timing card. This is a great example of it, where if you want to be able to integrate hardware physical timing into a system, you need a way to bring it in, you need a way to propagate it. This isn't common on a common compute platform. As shown in kind of the figure one, basically the picture itself is to way to make that either brought into the card or propagated. You generally have to have external cabling. In this particular case, it's SMA coaxial cables. I love the fact that figure one showed in order to propagate that, you actually have to have this little black line here. And it wasn't really labeled, but it's basically, in essence, a coax cable. So that's externally connected outside of the chassis to make this, passed on. I believe, and someone can correct me if I'm wrong, I believe from this figure one, it was this timing card is this guy here. And then I believe this was an NVIDIA CX6 for the particular application. That was what would develop for the timing card.
That's right. Yeah.
Yeah, and it did its job. I think, honestly, when I saw it, I was pretty inspired by it for some other aspects of things that I've been developing. But that's what I love about this OCP TAP group, is we all contribute things and it may scale into something else.
Yeah.
But this, in essence, the coax cabling is really what I want to talk about here as part of the problem statement. So how are you going to propagate that? Like in the case here, this is externally done. So you have an external cable done here. There have been some timing sync NICs that have been offered currently in the market. Some of them have U.FLs, others have MMCXs, but basically miniaturized version of coaxial connectors. One option, if you wanted to propagate timing, the physical layer timing within a computing platform, is you could use U.FL compatible cables to do that. These are very common. The ones you normally see these in are Wi-Fi routers, or in the case of a tower, if you have to connect them to an external antenna, you may see like a full height bracket with punctured SMA openings. I have one of those in a system in my lab today on how you're going to get the Wi-Fi signal out. So it's a very usable, common thing. The problem, if we're starting to talk about a telco infrastructure point of view, as well as a factory infrastructure point of view, is U.FLs are really great as long as it's a one-time, connect and you're done with it. They have what they call low insertion rates, which basically means the number of times you can plug and unplug them. In the case of U.FLs, they're generally rated around 10 insertions. But that's, like a bell curve number. That could be a few more if you're really sophisticated. And it tends to be, if you're thinking about factory installation, a lot less. You get one or two shots, and after that, it's probably not going to, operate anymore. More than likely, the U.FL will basically delaminate, which means it pops off the card itself. That creates problems. The other aspect of it too, especially if you're talking about enterprise infrastructure. So if this is a factory install, we have to basically create training information and installation notes on how these are going to be connected, how they're going to be routed, the fact that the links, depending on which card is where, may require different cabling lengths. So then it's just another sets of SKUs that have to occur. But then not only that is generally you want things to be field updatable and upgradable and repairable too. So then we have to replicate at least the same number of sets of SKUs for the outside world with the same level of training. And in some cases, these may not be the technicians that are coming from the actual developers of the infrastructure. They may be, third party, technicians. And so they themselves also have to get training. And generally what ends up happening, it just becomes a lower quality metric, which ends up turning into a customer dissatisfaction score. So we at Dell, and I'll try my best not to bring up Dell too often here, but I want to do it from a point of view so you understand. We have deployed a few of these in the past, and we generally keep it on the client side, the customer side of things. We try our best to avoid it on the enterprise side. It just, like I said, it creates quality issues and a lot of dissatisfaction scores with it. The other option is what's currently done today on several platforms that are in production. So in this particular case, what I've wanted to set up as an example, I actually have a couple of customers that I've been out to their sites, and I would love to have shared a picture, which unfortunately to get through all the legal approvals takes too long. So what I decided to do was take a one-use system that I have today. One of my partners that's in the telco environment on one of my NIC partners is Intel. So I borrowed two of their cards and populated the system in order to connect them together to kind of demonstrate how you would propagate physical timing between the two. I ordered some ruggedized SMA cables. These things actually exist. They're basically aluminum cladded cabling. And in my particular case, I had to hand shape these. And if you've ever used these, which, for this particular example was my first time to use them, you can't just bend them. They're going to snap. So you have to kind of hand shape them, like you almost have to kind of warm them up. And in this particular case, I wanted to be really low profile. So I kind of got the shortest ones that I could. That's what I've seen certain telco customers or telco providers utilize in this sort of scenario. More than likely, they get those actually, made by the vendor themselves. But for me, I had to kind of take a few minutes to kind of shape them out and then get them in there. One thing I'll mention too is while it's not a requirement, there is a de facto standard about when you're looking at like SMA connectors that you generally want about 1/4 inch, a finger room between the two so that you can get your fingers in there to screw them and unscrew them. In this particular case, that's not there, so I had to use a hand tool to get them to get in there. And the fact that you can't really, as a circle, go around them, it took a bit of time. It probably took me about 10 minutes to finally get this whole cabling setup done. I bring all that up because you can just hear all the nuances and the problems that can come from that. But that's how this would work. And just as kind of a demonstration, how this looks like in a deployment scenario. So imagine a particular wireless base station, cellular base station that's got 6 sectors. It's broken into three sectors broken into 6 antennas, 2 each. This is how this would potentially play out. In this particular example here, within these two cards, I designated the second slot as the PHC. So I connected the GNSS to this particular card slot. I put its primary and secondary mid-haul or backhaul links between the first two slots here. And then the other 6 antennas, I basically doled them out to the remaining slots. This is today deployed in the field. It may not be the exact solution. This is kind of a representation of what I wanted to show for this particular presentation. But in essence, this is how it's done today, folks, for a 3-sector wireless base station. So I bring all this up while what we've seen with the timing card today and what is being deployed today by several NIC vendors on how to have timing sensitive NICs, that the external cabling method definitely allows it to work, but there are challenges that may remain present. And in essence is what I've just described here is just, the additional installation steps, the additional quality opportunities for failure. These are things that, we've been seeing in satisfaction scores with telco providers, that they're very happy to start seeing this advancement in the 5G space, that we're bringing in commoditized computing infrastructure under the digital side of the base station. But there's a few things we still have to solve, which eventually led to the introduction of a couple of contributions that I want to have a little more focus on here. So these were pretty recent. The two of the form factors that I'm highlighting here is the OCP NIC 3.0. This is the MES card that you can see on an OCP server, OCP-based server. It's compatible with the DCMHS motherboard. As part of the version 1.5 release, we included new physical signaling actually on the connector itself. Additionally, this year, we also contributed a very similar feature set to the PCI's Ethernet, not Ethernet, PCI's form factor, which is called CHEM, the card electromechanical form factor. It basically is that stand-up PCIe adapter that we tend to commonly call it. There is kind of this misnomer where you look at like PCI Gen 3 to Gen 7, and that itself tends to refer to the signaling rate that's on the SerDes on the signal on the connector itself. Complementary to that, as they're advancing the signaling standard, they're also upgrading the CHEM, the card electromechanical form factor itself. So every once in a while, there's new inclusions of features. Now, while that's happening, it doesn't mean that a Chem 7 card has to be Gen 7 compliant. That's not always the case here. And so even though Gen 7 is still pretty new, these new features being added today are relevant basically to all generations, speed generations of any card, as long as it's compliant with this Chem 7 spec. The slides that I'm going to show here over the next few, I'm mainly going to focus on the OCP NIC one. The main reason for that is these are contributed publicly, so they're all publicly available specifications that can be referred to and cited against. On the Chem side, however, these are copyrighted information available to active members. So I'm not really going to show much on the Chem side. I'm mainly going to be focusing on the OCP NIC side, but just consider the fact that they were both jointly contributed. So there is going to be some similarities. So as you see in the OCP NIC side, just make some assumptions that there'll be some similarities on the Chem side too. All right, so what was contributed on the OCP NIC itself? There is, on the pinout, it's already very populated as is. They only had 2 extra pins itself, which we're trying to preserve for other advancements. But one of the advances that's been happening on the OCP NIC side, there's this sideband management interface called RBT. For those that are not familiar with it, is if you think about, like, say, on a PCIe adapter, there's something called SMBus or I2C to basically manage the card. For the OCP NIC itself, it introduced the concept of an RBT interface, which basically, in essence, it's a 100 megabit pipe. It's very similar to RMII. It's a way to an OCP NIC itself is a mezzanine card that's on the planar itself, and in most cases, an OCP NIC itself is basically a removable fixed LAN over motherboard card. And so as part of that, there's some certain standards about how to share the baseband management of a server across a link. And so if you're basically sharing that kind of external connection, you're going to want to be having it at a higher bit rate than say I2C. And so we needed something of 100 megabits. Well, I'm bringing all that up because as part of 1.3, which occurred, I believe around 2002 or 2003, we introduced a USB interface, which is 480 megabits. In essence, that's almost 5 times faster than the RMII RBT interface itself. And so we're starting to see where this particular interface is becoming legacy. So as a result of that, this kind of created an opportunity here where we could convert this interface, which has, as you can see, multiple pins. We wanted to convert that into a flexible I/O interface. So in this particular aspect, when the timing was contributed, we wanted to basically take over that bus and convert it into a timing infrastructure. So we can now pass in both directions frequency. We can also pass a sync signal. So that's 4 signals right there. And then we also have a general purpose input and an output as part of it. So what could be accomplished, if you think back to the timing card, it had 4 cables, 4 SMAs. We basically replicated that. But we also wanted to provide some sort of alarming signals as well. By doing this, it in essence solved a couple of things. 1, it helps eliminate a cable. 2, one thing I didn't mention with coaxial cables is it actually plugged in? So there's kind of the concept of a presence detection. That's just not really, it's really difficult to do with a coaxial connector, but it's easy to do on an edge type connector like PCIe or this particular OCP NIC. There are card presence connections. So we know that it's fully inserted. So that's another issue we have with coaxial cables, is it actually fully seated or not. We now have a way electrically to monitor if there is presence capability. So that's another thing that we, in essence, have solved by the contribution of this particular feature. It is a little bit programmable. From the frequency point of view, you can set it to allow for what we know as EPPS or 10 megahertz. Basically, EPPS is an amalgam signal of 10 megahertz and 1 pulse per second together. For those that haven't seen it, it was a contribution of another company had made eons ago, and basically opened it up as a de facto standard. And what it does is it basically takes a 10 megahertz signal, and at the 1 pulse per second time point, it basically changes the duty cycle of that particular wavelength of the 10 megahertz signal. And so it'll basically either adjust it down or adjust it up. And you have to have basically the timing of basically PLLs that can interpret that. And it's a way to present both 10 megahertz and a 1 pulse per second on a signal length. In this particular feature set, we can actually support both the EPPS or the 10 megahertz. There's also a sync signal. The purpose of the sync is, while it's not fully stated, we generally, in some applications, we have to have 2 clock domains, one for the PTP clock domain, and then the other for synchronous Ethernet. So we wanted to be able to have the ability to propagate across the edge connector, both clock domains. And then lastly, the GPI, we wanted to give a way to have a physical loss of signal or a loss of lock to hasten the notification that a signal has been lost. We have a GPIO defined, but right now we don't have a specific use case for it, so it's kind of reserved at the moment. Yeah, and so Essence, so that was contributed actually by Dell in 2024, and several companies came in and made refinements to it. So this is a fully community contribution that's been ratified by the OCP NIC standard, and it's been deployed since 2024. And while I can't really state, with specifics, I'm aware of several companies that are developing product that benefits from this particular contribution. So over time, you'll probably see more discussions about that. On how this works, so given the fact that it's a flexible interface, one of the things we want to do is ensure backward compatibility and how to detect what if someone plugged in a non-telco card versus or a time-sensitive card versus a regular one. There's something known as, there's different names for it, but colloquially it's called like a through record. In most cases, what you'll see on enterprise capable adapters is the presence of likely a serial EEPROM that could be read on the I2C bus. And what it is, it basically stores a set of contents. Most cases, it's mainly about things like the serial number and the model of the card. But it's been augmented over time where it also has feature capability. So on the OCP NIC side of things, there was an addition of a new through record. Through, by the way, means field replaceable unit. So there was an addition of a new through record that allows for a system to actually detect as it's starting to power up what this card is capable of and what feature sets it has of it. Within that, the premise of it is the system needs to kind of detect it, determine if the system itself, as well as the card itself, are capable of these sort of features. And once it does, it starts enabling these set of features. The main goal of that is to ensure not only backward compatibility, but also to prevent damage. One of the things that we tried to do as we were contributing this feature was, as we were basically leveraging this RBT bus, is we also wanted to make sure that the directionality of these signals are compatible, so that if you just have some bad code that does a bad check, at least it won't damage the system if it's starting to be brought up as it ends up not being compatible. So there's a lot of foresight that many companies came into to ensure that as we're adding this feature on top of another bus, that we were not creating a damage opportunity. Because the goal of this feature was to reduce quality, not to create a different set of quality issues. So on the chem side of things, like I said, I can't really talk too much about it. If you're an active member, most of that documentation is online. You can pull from it. But I will say, as a contributor to it, my goal is to ensure that there was a lot of commonality, because I want to ensure that not only on the system side of things, we want to be able to have a similar sort of look and feel, but I also wanted to make sure that the NIC providers that are developing their hardware as well as their chipsets, that they're not having to have two different sorts of feature sets that they're having to accomplish, that there's some commonality on how to basically create and develop and deploy. So that's about the last I'll say of that, unless anyone had a question before I start moving on to some use cases here. All right, thank you. So how this works. So it's one thing to kind of start talking about what we've added. I want to at least have a couple of slides that show how it's used. So in this particular use case, this is just showing two OCP NICs. So think about like that timing card, figure one. How are you going to get the information, the physical timing from one card to the other? Before, it was external coaxial cabling that was propagating that over. In this particular case, while not every circuit is shown here, what we're trying to show is the fact that the frequency and the synchronization, so in this case, time would be represented by the frequency, and then sync E would be represented by the sync. Both of those are propagated into the motherboard. The motherboard may or may not have its own PLL or buffers. It may literally physically just have traces. You can in theory just literally route traces if you just want to go from only two slots, one to the other. and then you just designate which one is the leader and which one's the PHC and which one's the follower. But in essence, that's how, instead of using external cabling on the front bracket, that is getting now passed inward. Again, that just solves a cabling challenge. It solves a presence detect. Is it seating challenged? It makes everything very nice and clean on this particular use case. And in essence, I'm aware of several developments that are using something like this. It is a very, very, useful feature.
Jason, is this a smart NIC?
It is not a smart NIC. It could be a
Okay.
really basic NIC. You can literally be ignoring the fact we're talking about G 8275.1, it could literally be a 1 gig base T NIC talking to another, propagating timing to another 1G base NIC or 100 base T, NIC. It could be as non-smart as it can be. But I will say too, it is hardware. So it's not a cheap card. If you're actually implementing timing, more than likely you're putting down extra timing infrastructure to do that. And I will say, just as a personal, I've been at various companies. I will say there's a lot of gross margin in a lot of those timing ICs. So it's not cheap sometimes. If you want to hit, G8275.1 and .2, you want to be very intentional with it. It's not just something that's really simple. But I believe as you start implementing feature sets like this, and you start creating use cases like it, people will compete. And then the market itself will dictate, the proper pricing on how these things should be properly priced. Good question. But yeah, it's not just a smart NIC, but it could be. There are some things like called as RAN DPUs or L1, L2 accelerators. They themselves can also benefit for a feature like this. I also wanted to mention PTM. In theory, with PTM itself, the whole premise of it is, in order for it to work, you need both NICs that are compatible for PTM as well as a CPU that has PTM capability. I have seen several presentations and several papers talking about how PTM can be enhanced if the 1 pulse per second from a particular CPU was connected to the NICs themselves, that the NICs themselves, as they are doing timing correction, could potentially improve their accuracy. So I have been working with a couple other companies that are looking to see if they can create a new feature benefit, basically, from these particular contributions, both on the OCP NIC side as well as the chem side, that the PTM is great, but it could be better. And there's a bunch of other amalgam of different ways to do it. And in essence of time too, I really want to start talking about kind of the next things. Much of this hardware now is contributed. It has been scrutinized, and it's now in either development or in production today on using these fixtures. The next area that I want to start seeing, and I've been really trying to promote, and I'm asking for everyone's help here as timing subject matter experts, is to start looking at how we can take this contributed hardware capability and start looking to see if we can make software contributions that benefit from it, which will then further scale how we're using things like PTP4L and other essence of how these particular things work. So much of what I've kind of demonstrated has been on a hardware, and it's very, I will admit, it's very focused on a server-side environment. But there's other BIOS and Linux OS level applications that need more development to be able to use this, to scale it. Make sure I'm hitting my notes here. Yeah, so I've already said this before, that the form factor itself was defined mainly to kind of protect the system itself. Now we just got to make sure that it's being able to be used. And then the last thing too is much of timing synchronization today What we do in the hardware side of things, a lot of it's done what we call out-of-band management or managing hardware internally. But much of timing synchronization is done in OS. And so it is kind of its own domain if you're looking at from a timing perspective. And so much of what I'm going to show here is about NOS improvements that I've been talking with several companies and trying to ensure that we further this along. One area, if you look at how you discover, so you buy a NIC, it on the data sheet itself, it claims to be IEEE 1588 compatible or other timing synchronization. So how do you prove that? What most people do, besides Googling, is eventually you run across a lot of field manuals. I would mention it seems like Red Hat is doing a good job on their Google AdWords or their scoring because they tend to be the manuals that show up the most. I think I pulled maybe this picture from one of their available manuals online. But basically, there's a common method that you can find if an Ethernet a NIC itself is timing sync capable, is etool dash capital T, and then you point to the Ethernet number. Generally, it'll demonstrate it's 275.75.1 and 0.2. Is you also need synchronous Ethernet or the E synchronous Ethernet capability. I'm not going to try to test all my my G knowledge here, out loud, but I have seen a couple companies contribute basically syncy capable code on various GitHubs and basically open repositories. I think that's great. That's really awesome. I think I'd like to start seeing some of those kind of come together, having an organization help kind of shepherd that along. And right now, both of those need to kind of interact with each other. Today I just kind of grew a random green blob here. I don't have any specifics that it has to be this, but in essence, these are some of the missing gaps on how to make a G8275.1 capable software solution happen. Is if we can implement some time sync control, a PLL manager, an ESMC manager that handles the G8264 messaging. Those are some gaps that I'm seeing that are not part of a multi-company contributed sort of solution. It'd be nice to start seeing, those keep shepherding along, and ultimately getting those contributed upstream into either Linux or something compatible to that. Lastly, as I make sure I hit all my bullets here too, the NIC drivers themselves, I think most cases, a lot of this is specific to the vendor themselves. It would be ideal if we start looking to kind of make either de facto or more standardized versions on how their APIs are going to handle time sync capability. Above all, the reason I'm saying this is we want to see features like this scale. And the only way you're going to make it scale is you have to have companies willing to come out and contribute and work together to make something like this happen. So lastly, I'll say, as I've shown you, and I'll say with high certainty that the NIC specifications, those contributions have been out for a couple of years now. They've gone through several levels of scrutiny. They've become pretty stable, and you're going to start seeing here, while there have been some deployments with it today, you'll probably start seeing some more public, blogs and articles about it happening. We're now at a stable point where these particular feature sets are allowing people to develop NIC and system interoperable hardware. But like I said, the thing I would like to leave the audience with is your areas of expertise where you see opportunities on the software side of things. If there's areas that you can help either contribute or influence, I'd like to see your help too. And please reach out to me. I can kind of help, with that messaging, but just trying to see if we can move the software side of things. I think what we've done today with eTool itself and PTP4L itself, I think there's a great, what has been contributed so far for synchronous Ethernet type features is great too. But we want to see that push. We want to see the stuff scale. I mean, the fact that you guys are interested in this particular project under OCP lends benefit that there is definitely good interest in things like this. You guys want to see this sort of stuff happen. And so where I can help you, let me know. and I definitely need your help as well. So that being said, I really want to thank you guys for this time that I've had with you. Yeah, thank you.
Wonderful. Let's open the floor for questions.
So Jason, really good engineering. I see what you're doing, and I like it a lot. My question is, when you talk about latency, as you can manipulate it with Python, are you talking
Okay.
are you talking about one-way latency or the two-way latency?
Specific to one way, but in essence, it is both, because there's going to be, from the IC of this particular NIC to eventually the motherboard, there needs to be definition of the length, as it's, see, now you're stretching my knowledge. It's on a PCB trace. It's 180 picoseconds per inch of trace. So I mean, there is a defined amount of time. If we're trying to shave into picoseconds or nanoseconds, that has to be defined. And so what we want to see eventually happen is the definition of that propagation delay, both on the ingress side as well as the egress side, across all the available capable time sync links. And in essence, basically have it somewhere like ETH-tool. If not ETH-tool, maybe in the BIOS. There's ways to do advertisement in the BIOS. There's different ways to accomplish this, but basically some way that it can be seen in OS. So in essence, that software like Python or something else can see it and interpret it and then use it.
So one of the things that we've discovered and we've talked about in previous OCP meetings is that it's impossible to measure the one-way speed of light. That's the
Yep.
physics. So if it's impossible to measure the one-way speed of light, how can you actually use the one-way speed of light? I assume that you're assuming that there's a simultaneity plane between the one of the senders and the receivers, but we know that simultaneity is a problem, and that indefinite causal order in physics will thwart that computation.
Yeah. What I'm going to answer with is, Paul, I have no idea. But what I will tell you specifically here is there is an allowable level of latency to make equipment like this operable. The conversation I'm having with you right now, Paul, from my Bluetooth headset to my laptop, and you can get the essence of all the tributary to eventually get to you, Paul. There's latency, right? But we can actually communicate. So in this sort of hardware, in this particular cost, level, you're going to still have nanoseconds of latency. Where we can shave is beneficial, but it's going to be there. I cannot talk about what I've seen some of the other presentations on, how to do it across Mars, get it to Mars and everything. You have to get someone else on that one. I apologize.
No, it's okay. It's not intended to be a trick question, but it's intended to illuminate some of the interesting questions about how do we deal with ordering of events, down on the bits on the wire compared to what we're offering, say, a database programmer who wants to do transactions. And one of the interesting insights that came up literally in the last year or so was from Edward Lee, who was pointed out that clock synchronization error is indistinguishable from latency.
Okay. That's good to know.
I won't hog the conversation, but I want to listen to the rest of it. And thank you for a great presentation. And
Yeah, thank you, Paul.
And Jason, I will reach out to you after the meeting.
Yeah, sounds good. Thank you.
Jason, I've got a couple questions.
Hey. Yeah, please.
Hey, okay. First one is, how much has Dell budgeted to do some of this work you're talking about?
When you say budget, what do you mean by that?
Is Dell, are you putting your money where your mouth is to build some of these open source tools, or is it just one of those things, well, somebody else should do it?
No, that's fair. Well, I've been budgeted from a resource standpoint to contribute these sort of features. So these two particular contributions, I help lead both on the OCP NIC side as well as the PCIe chem side of things. We have a division that's really focused on winning and delighting our telecom customers, as well as one of the things that Dell is an ecosystem partner with a lot of different companies, not only in hardware, but also software. So it's not only just our investment in it, it's also our hardware and software partners that are involved in this. I can't myself particularly, I'm not really authorized to say which names, but you can see
Okay.
various press releases. Yeah, but
Yeah.
we are continuing to go quite a bit into this 5G space because we want to win the server business within it.
Yeah. Okay. That's a good answer. Now, the other thing that you didn't bring up is observability. How do you have any tools, or are you considering any tool to monitor the offset of all the servers in a system, be it within a data center or over a 5G network, and report both precision, that is, the standard deviation of all the servers, and accuracy, how accurate they all are, at least compared to each other.
Yeah, I will say from an observability, from where Dell's point of view is on what we're offering, as well as some of our complementary hardware partners, is we can offer observability of things like what the features are capable, the trace latency that are defined within certain particular specs that have that information from a static, generalized, and I'll say generalized point of view. It's believed to be nominally, but when it comes to a real-time point of view, that's really where it gets into what I was discussing on kind of the software use cases. What you're actually talking about is really what we need to see more of to benefit from these features. Everything that you're asking is basically what I kind of amalgam into this slide is what are we going to do here to augment not only the open source sort of things, but also the current paid solutions too. They all need to basically leverage these features. It's really going to be in those areas that you're going to see that observability.
Okay. One issue there is a diversity of manufacturers. Have you looked
Yes,
into the Yang netconf models for PTP and NTP?
I have not. But I
Okay.
will say diversity, I'd like to see more of it.
Do
Not
you know
from a hardware
do you
point
know
of view and software.
do you know the Yang netconf model?
No.
Okay. Think SNMP MIBs, only Yang is yet another next generation, so it's the newer version of an SNMP MIB. There are ITF and IEEE models for Yang, at least up for approval. I'm not sure if they're solid yet, but
Okay.
so and in those models, one is a model for configuring the device, the other is a model for monitoring the device. So that
Nice.
seems to hit both of your concerns and could give you a general GUI for, well, not anything, anytime, anywhere, but at least a general GUI. People could be, some of your customers, I'm sure, would force their vendors
Yeah,
to conform to.
that makes a lot of sense. I appreciate that. Thank you, Hank. I'm going to look into that. Hey, Sidharu, I see your hand is up. I don't want you to lose time here. Speaking of time. Hi. Sidharu, do you want to ask a question?
So while we're waiting for Sidara, I can possibly follow up on this question about Yang. We have a work stream in the Open Atomic Ethernet, which is held on Mondays, which is discussing the whole bring up process from a chiplet perspective. And one of the things that we've discovered is there's quite a lot of shortcomings in a lot of the standards around, particularly around MEBs and around Yang. And we're in the middle of discussing that. That would be great if some of you can join us perhaps on Monday mornings at 8 a.m. On the OCP channel. It's really interesting because being constrained to thinking about legacy, unfortunately, is too small a box to thinking if you really want to design a standard like Ethernet that's going to last another 50 years, for example. So we're open and would look for people that contribute as well as participate in that debate.
That's a good thing for everyone to do. Thank you, Paul.
Paul, could you put a link into the
Chat.
the chat?
Okay, I'll do that. Thank you, Hank.
Before we lose time here, Saharu, did you want to try again or see you back on? No worries. Hey, thanks.
He's muted.
Hey, thanks a lot, guys. I know we're kind of hitting time here. Or between PG, share some examples, please.
Kevin, Kevin Bross, do you want to ask a question?
No, I was just going to say, Siddharad, you put something into the chat.
I see.
Yeah, I don't really have much more to kind of share than what's
One thing,
here.
Jason, I wanted to ask, and that is about NIC 3.0.
Yeah.
In 68 and 69 or 69 and 70, I forgot, like the one that I don't know what they're usually reserved for some other things. I don't know, like, I mean, I didn't follow what happened with Damien. Like, did we end up like putting them optional or something that you can make them PPS in and out and things like that?
Yes. Yeah. So it's an all an optional sort of feature. Much of what is in the OCP NIC, there are some mandatory features,
Yeah,
such
flexible.
as you need to have PCIe capability, but these are flexible. So not everyone has to have this capability.
Yeah. Okay, great. Yeah, because that can be like easily for routing inside the motherboard too, like things.
Exactly.
In the absence of like, I don't know, like the panel space, like you don't have that much space there. Yeah.
That's exactly right. Yes.
All right, great. So if no more questions, is there any more questions? Last question? Hearing none. All right. Well, again, thank you again, Jason, and we'll see everyone in 2 weeks. All right.
Fantastic. Thanks for your time, Jason.
Much. Thank you.
Thanks,
Bye,
Jason.
everyone.